All right. Okay. Welcome everyone, and I'm very excited to be at the first meeting for the zero knowledge study group. Welcome everybody here, and this is going to be a series. So if you miss the first one, you can always join us later, and everything will be recorded and with all the study notes. So yeah, I want to make this interactive, so it's not just me talking to you. So because it's supposed to be like a peer-to-peer fashion as a Bitcoin fashion. So if there's any questions, anything, just feel interrupt, and let's make it more like a forum-based discussion. Okay. All right. So I think from today on, I'm going to start a series. So basically assume you have no prior knowledge about so-called zero knowledge proof. And I'm going to, hopefully when you finish the whole series, you can become from zero to hero. So that's our objective here. And this is a evolving topic. So I think this can go on forever as long as the research of or development of zero knowledge, has, unless it ceases to exist one day. So we can always keep this as a recurring thing. So, since this is the first time, I just want to give the very high level idea, understanding of, everybody present here, what's your background? What did you not just in terms of zero knowledge? Why are you interested in it? And also, what do you hope to learn from this, get out of this? So Brandon, do you want to just get a quick start?
Yeah, I can start. I'm a developer at Handcash. I'm interested in zero knowledge proofs, like specifically for like unique applications. I think it's the identity use case is really interesting, and it seems like the best. Like if we're gonna live in a world where you need to identify certain things, it seems like zero knowledge proofs is the way to do it. And it just seems like a hot topic, so I want to get an understanding. I don't know much about it. I read the introduction material in your GitHub, but I hope to understand how to deploy them on Bitcoin practically, and like how to use them.
I see. Great. Okay, welcome Manikan Jun. It's late there, right? Welcome here. Yeah, he's our
Hi, Shah.
Hey, he's you are the Bitcoin ambassador in India, right?
And that's right. That's right.
Okay, great.
But it's a pleasure to be here.
Yeah, it's a pleasure. He got a new citadel in Bitcoin citadel in India, so that's very cool.
Yes, supposed to be inaugurated on the 16th of October. So looking forward to it.
Okay. Yeah, since we are already talking, do you want to say a few words? Why are you interested in this topic, zero knowledge, and what do you want to get out of, learn from this and get out of this?
I'm a physicist. My background is in theoretical physics, molecular physics. So until last year, I was in Berlin doing my PhD, and then my work is all done, but I did not, I have to still defend my thesis. But I got so interested in BSV that I jumped right into it. So my interest in zero knowledge proofs right now is that, for one, intellectually, it's the most challenging thing for me, very interesting with the world of possibilities. And secondly, I'm not a developer. I mean, I understand code and I can write dirty code and get something to work, but I'm not a developer and I don't want to be a developer. But I want to fully understand how these things work, so that when it comes to designing something, designing a solution, or when it comes to interacting with a developer, I would like to be fully into the thick of things.
Nice. Okay, Samir, you want to go?
Yep. So I'm basically currently I own a company, and I'm just here to learn about like how the zero knowledge proofs really work. So for example, it's really fascinating for me because like how do how do I know somebody else whatever the solution has been done is actually valid, and how do I prove that? So that's, I mean, without knowing other party, how do I know that proof is right is something really fascinating. So I think I'm more of a philosophical guy. I don't know. So I'm trying to understand the philosophy of how that really works, and then how you apply that to the development, the development on Bitcoin, and how do you connect that. So I think that's what I really wanted to know. So yeah, so that's why I'm here.
All right. Hey, Zach, how are you?
Doing well. I didn't know this was happening today. Otherwise, I would have been prepared to be on camera. But thanks for hosting these, man. I'm really excited.
Okay, yeah, you are the first one to try out our zk Battleship tutorial, so that's great. You want to quickly go over like why you interested in zero knowledge, and what do you hope to get out of this study group?
Yeah, absolutely. For me, it's we're building a future where everything is on a single ledger, potentially, not encrypted unless we choose to encrypt what we're writing to the ledger. But from a personal and business perspective, I really like the idea of being able to write as much in plain text as possible. I use the example though of if you were a woman who was going to school in Afghanistan, let's say you were a young girl going to school in Afghanistan in 2010, 11, 12, and now you're in high school and ISIS takes over the country, and the things you've been doing, just plainly going to school, become illegal. Is there a way that, knowing we're going to write records for the school to blockchain, that we can protect the student in the future against an unruly leadership, government, or faction? And so to me, zero knowledge proofs allow us to document the things that we want to document and to have as provable, irrefutable evidence of things that happen, but only make that information accessible to either third parties that we trust, which would be applications, or more likely people that we trust in the real world. So to me, this is an invaluable component to building the type of trusted future that I'd like to live in, versus maybe some of the nefarious ways that people would want to use our data.
Sounds awesome. Yeah. Okay, Dave, you want to give it a go?
Yeah, I'm Dave. I'm an independent Bitcoin developer. So what I'm looking for is, so I want to understand what kind of proofs we can build with these circuits, I think you call them. Like I heard someone say that you can only prove true facts or things that are truthy. I'd like to investigate that. And also have you talk about at some point the additive nature of these proofs. So to kind of understand how you can prove something and then build on that proof in the next step. That's kind of fascinating to me. So just kind of the general use cases that we're all kind of interested in, and then the drill down into the tech.
Okay, sounds awesome. All right, Brad, last one.
Hi, everyone. So yeah, I am Brett Banfi. I'm the community manager for the Bitcoin Association, as well as sales and outreach and development for Handcash. And my interest in these sessions is from mostly just my personal knowledge. I just want to learn about this. I don't have any background in developing or coding or anything, but I like to understand how things work. And so I'm looking at this for my own personal knowledge.
Oh, zero knowledge. Okay.
I'm trying to get as little knowledge as possible. I want to empty my head.
Zero. Okay. Then you have become the guru. Okay, sounds great. I think it's awesome. I think now it's just make this, you guys probably just elevated the scope of this group. So I'm really glad. Yeah, a lot of people for variety of reasons are interested in this. I'm personally always, trying to learn new things. I think that's also, and I want to shift the Bitcoin, of course, the culture towards more like a hacking and just tinkering and building kind of things. So when developers come in, they can, other than the drama and all the, suing this, suing that, I think that there are a lot of people, they'll be more interested in, tools and libraries and functioning apps they can actually use. Then that's my overall goal. So I think this is one big part of that. So I want to just keep driving that. So let's get started. So I think today, because this is the first session, so I want to, just give a very high level, like 30,000 feet, bird view of the whole thing. And then we can dive a little bit because, we can focus for the beginning. I want to, focus a little bit on the applied zero knowledge side of things rather than the theoretical. I think later on when we have more time, and if you guys are interested, we can dive into more like a math heavy theoretical side of things. But for today, I want to more focus on the applied side. So, at the very beginning, people will ask like, what is zero knowledge proof, right? I think I always give this analogy. I like this. So basically think about, you have probably many of you have heard about this game, right? Finding Waldo. So basically you have a picture, you have a sea of people. Maybe here you are showing some ski resort, maybe it's Lake Tahoe, maybe it's Colorado, whatever. And then you want to find this specific guy called Waldo, and he dressed in this way, and but there's like a sea of people who look like him. So the idea is to find this guy. So in a typical game scenario, you just find this guy, and then that's a game over, right? That's end of the game. But what if you want to, let's say Alice, wants to prove to Bob, hey, I know where Waldo is in this picture, but maybe it's because it's bragging right, or maybe it's some competition, and then for whatever reason, Alice doesn't want to show exactly where Waldo is. So the objective here is to say, hey, I'm Alice, I want to prove to Bob. Usually in zero knowledge sense, we call this Alice, this is the prover. The prover, and Bob the verifier. So Alice wants to prove to Bob, I know where this guy is in this picture, but I don't want to give out the exact location. So how is this possible, right? It's a little bit counterintuitive because you are trying to claim something is true, but you are not telling, exactly, you are disclosing that thing in particular. In this particular case, it's just Waldo's position. Right? So one way to do it, Alice I can just, I don't want to, probably a lot of people have ever seen this. I'm not just to hide this as a secret anymore. Anyway, but what Alice can do, she can grab a big, gigantic, like a board. And then in the middle, she cuts out, the shape of Waldo in the middle. And then what she can do is, she move the whole full picture. So, she then place the board somewhere, right? And then Bob will stand in front of the board, and then Alice will step behind the board. And then she moves this picture in a way such that, Waldo will shows up. Okay. Sorry, I think somebody's, give me one sec. Sorry, I think is this a UPS or somebody? Give me one.
That's funny. Always at the worst time.
Important package.
So in this example, like you have to make a couple of assumptions, right? Like as in, Alice isn't taking Waldo from like another page. I wonder how that translates to like an actual ZK proof.
It's a really good question.
So what is like Alice caring about Bob? Probably, I don't know. I think she's not carrying anything, right? So she's carrying the whole the ledger. I think probably just the header of the ledger. I think that's gonna help her prove. So it's a small set of data. It's not a whole long set of data either. So yeah. So that way it's easier to like, yeah.
Go ahead.
So no, I was telling like if you're carrying of Bob, everything that is not Bob, then it's easier to verify whenever it's Bob, right? So is that the way you're solving this, Chave?
I'm not quite following you. What do you mean? Like, why does Bob matter here?
Oh, I mean, so it's between Alice and Bob, and Alice is trying to prove to Bob that without the information, without the knowledge about Bob, he's trying to prove that Bob is, I mean, Bob's transaction is valid. Is that right?
Not knowledge of Bob. She wants to hide from the information from Bob. It's not she doesn't know Bob. The knowledge is about the secret location of Waldo. It's not anything about Bob himself. Does this make?
Oh, okay. Yep. Okay. Yeah, makes sense.
So the good thing about here is, if Bob can see from the, in the middle of this hole, he can see Waldo, he can be sure, right? This is so-called, complete list of the zero knowledge. Basically, if Alice does know this position, she can convince Bob, right? Because if she doesn't know the position, there's no way he can move. She can move the picture such that, Waldo will show up in the middle of the board, right? And at the same time, it hides the so-called zero knowledge property. Right? So basically, even Bob can see, Waldo shows up, but because his view is blocked by the board, so he doesn't know exactly the location. So you pretty much kill two stones with one bird. Alice shows, Bob, convince Bob, she knows where Waldo, she has found Waldo in this picture, but also at the same time doesn't give out the exact location.
I made the comment when you left asking, so you're making the assumption that there's one picture, right?
Mm-hmm.
So there's no way I can compete with like multiple pictures of Waldo.
Mm-hmm.
How does that translate? Like, is there like some initial state that everyone agrees to?
Oh, I mean, that's then you can do all kinds of this is where the analysis kind of become loose, right? So in reality, you can do all kinds of things, right? For example, right, you can, if this you want to make sure this is the board, right? So you can say, hey, how would I say? So you can say, in the in the extreme example, right? I mean, Bob can say, hey, let me, get some Scotch tape and then tape this to Alice's hand, right? So she can make sure she cannot swap it, or make sure when they set up when they set up, so they want to make sure there's no other picture inside. They can be an empty room, that's a part thing that in the physical setting you can, but in the better way in the zero knowledge, because everything is math, so you can even be more confident than you really, because really you made like a magician, right? But let's not go to the extreme case. You see what I mean, right? So you can have all kinds of measures, to make sure Alice not faking something. Yeah. But yeah, good.
Okay.
Good. Yeah.
Is there like a term for that? Like, is that the setup? Like the.
Oh yeah.
If you're patting Alice down, that the.
Mm-hmm. Yeah, almost
Okay.
similar. I think that in a certain type of zero knowledge, which I think which at least for the first few episodes, I think we're going to concentrate on. It's called zkSNARK, or some other, zero knowledge protocol. They usually have this, like a setup that both parties have to agree on before they carry out the proof. So it's almost similar to like you are like inspecting the board, or you are making sure there's only one picture, and there's nothing up in the sleeve, right? So it's almost this way, like the prover and the verifier, they have to agree on. They call it the common reference screen. So basically they have to agree on, hey, this is the setup, and we can, once we agree on this, then we can carry on the proof process. I think I'm going to, in the next few slides, I'm going to cover this in more detail. Okay, is this analogy now clear?
Yes.
Okay, sounds
Yeah.
good. All right, then let's keep, let's go to the other very popular real world zero knowledge. And so, in Bitcoin or many other so-called crypto, right? So if you have some coins, you want to move it, and you want to, let's say, Alice wants to move to Bob, right? So Alice then she has some coins that's locked to her, almost like a public key. I mean, that's not what about address. It's almost the same, identical, right? Equivalent. So Alice has some coins locked to her public key, and the way she proves she owns this coin is to say, hey, I have she wants to prove the knowledge, she knows the private key, right? But here's a trick, right? She cannot just give out the private key and submit it to the blockchain, because, then everybody can see it, right? And it's supposed to be private. And then anybody who can know this private key, if there's any other coins locked to it, they can just steal his other coins, right? So the way, this is almost everybody uses this in crypto every day, but they don't think about it. But this is almost the most famous zero knowledge proof in practice. So Alice is trying to show, I know a private key corresponding to the public key, but in a way, she does not give out the private key, right? Because otherwise there's a lot of trouble coming. So what does Alice do? So Alice produced this so-called digital signature, right? So you can think about this as another type of zero knowledge that Alice can prove she knows the private key without giving out the private key. And if the digital signature algorithm verifies, checks out, then we can be sure Alice knows the corresponding private key. That makes sense? Any comments, anything here? Okay, yeah, just a side note, I think this, that's, if you talk to like a cryptographer, he may not totally agree, because you may have some like a theoretical, aspect saying, oh, you are leaking a little bit of information. If Bob can choose some like plain text or whatever for Alice to send, but yeah, for here, let's keep it, high level, and then don't get too distracted by the theoretical things. So
no, thank you for calling us out, because I think this is easier for us to explain than Battleship.
Oh yeah,
everybody in crypto has already used public and private keys and probably has a concept of a message or a signed message. Battleship is a little bit next level.
Yes, I think so if it's people who are already familiar with crypto, I think this is my favorite example. And the last one is if you are coming up with people who have never touched crypto ever before. So this is the example I would give out to non-crypto people. Yes. Okay, anything else? Okay, if not, let's keep moving. So I just give you two examples, on what zero knowledge proof looks like and what you can do. And next, I think I'm going to dive a little bit into the, what are the, we talk about zero knowledge proof in the blockchain space, right? So what kind of zero knowledge proof? That's the most popular and the one we most focus on today. So it's for guys who have been in crypto a little bit. I think you probably heard about this term called, zkSNARK. So this is probably the most widely used proof, zero knowledge proof. So here's the thing. So zero knowledge proof is, it's a big field, right? There are many ways to do it. I think I just showed, for example, digital signature, right? You can think about that's one way to do zero knowledge, but there are many algorithms or protocols to do this. You have SNARK, you probably heard about stack, bulletproof. There are many variants, but so far the most popular one, I think I'm going to talk about why it is so. But at the big, for now, you just want to say this is the most popular way to do zero knowledge proof, at least in the blockchain space today. So there's a number of reasons. One is, first of all, I want to talk about, what's a SNARK means. So in the terminology is a little bit of esoteric. So zk means zero knowledge, right? S means succinct. I think that's why a lot of people prefer to use this scheme. Succinct means two things. One, the proof size is very small, okay? Because, blockchain space, right? We're trying to, reduce the size of things that were put on the blockchain. So this is very important. The succinct, short proof, but also means the verification is also very quick. I think maybe because of the math and also the proof size. Basically, doesn't matter how complex the problem you are trying to prove, you can always verify it within most time, just tens of seconds, milliseconds, sorry. So it's very quick. That also means because it's very easy to verify on chain, you can put it on chain and verify it over there. That's, I think, the number one reason that people try to use this scheme. And it means non-interactive, so it means, the prover just send one short message and ends up on chain, and then everybody who wants to check it, everybody can be verified. You can just run this through this mechanism, and you can be sure this proof is valid or not. And ARK, I think I'm not talking too much about it. Argument of knowledge, so pretty much just knowledge. So we don't worry about that for now. So this, I think Brandon just mentioned a little bit earlier. So in the Waldo example, the prover and the verifier, before they carry out the proof and the verification, they have to agree on certain type of common setup, right? So this is similar here. So usually zkSNARK consists of 3 steps. And what's a high level idea? What is trying to prove? I think that's also a little bit, Dave mentioned a little bit, what kind of things we can prove. So in a theoretical side of things, so you can think of the statement zkSNARK can prove is, arbitrary function. You can think of this as like a mathematical function, f, right? So think about math, right? Function. You can say square, you can have square root. You may even have, let's say, Fibonacci sequences. Right? These are all mathematical statements. You have inputs, and then you have outputs. I think the only unique thing about here is because we're trying to just check if the proof is good or not. So it's a so-called, the function has to be a predicate. If you're familiar with, go ahead.
Sorry, what is the technical term for this G?
You mean in the first one?
Yeah.
Generator.
Okay.
Yeah.
Thanks.
Okay, we haven't reached that stage yet, but anyway.
I'm really sorry.
No problem. So, it's the only thing unique about this function is, it returns a Boolean. So it's almost very similar to Bitcoin script or smart contract. you know, if you're spending a coin, you make sure this predicate must be certified. So same here. And also when you have inputs, you have two types of input. You have X, which is input that everybody knows. In this scenario is prover and the verifier. So they both have to know. And I'm thinking the key information here is W. It's called private input, but also, you know, in the literature, it's been called witness. So basically means this is a secret you want to keep. The prover wants to hide from the verifier, but still able to convince the verifier, hey, if you put this inputs into the F, it will evaluate to true.
So in the Waldo example, the picture is X and the location Alice knows is W.
Yeah, you can that's one interpretation. Yes. I think that's a little bit of not confining to here because we're talking about math. So that's where the analogy becomes a little bit obscure, you know. So here you can say, oh, W can be the coordinate, right? X, yeah, as you can say, right? X can be the whole full picture. The X is the coordinate, and the F can be say, hey, if that's a Waldo in this position in this X. So yeah, that's one way to interpret it. Yeah, actually, I've never thought.
This makes more sense in the battleship example.
Yes.
Where the public input is the state of the board and the private input is your yes or no, or the state of your side of your board. Or you're looking for a single coordinate. In that case, it's one input and it's either a yes or no response.
Mm-hmm. Yeah, I think
got it.
Yeah, this is like just a pure theoretical side of thing. So even to just give out more information, you know, I think Dave may be interesting. So actually the zkSNARK is also very popular because you can prove actually for any NP statement. So NP, for people who have not heard about it, it's a non-deterministic statement. So basically pretty much all the computational problem we are solving today using a computer, you can think about it falls into this category. So that means pretty much every computer program or every computational problem you are doing, you can prove it in a zero knowledge sense. You know, you can talk about 3 colors. You can talk about, you know, let's say a traveling salesman, if this is the shortest path, or you say, yeah, you can pretty much all the practical computation problem we are facing today, it can be proved using this zkSNARK. But of course, you know, you have for different, depending on the exact problem you are proving, so you may have different, you know, complexity. So that's I think where the prover side, I think that's then. Guys keep coming. Okay, anyway, let's go to the 3 steps here. So as I mentioned earlier, so usually in the zkSNARK, you have 3 steps. So at the first step, you have a setup phase. You know, that's where the prover and the verifier both have to agree on this process. So what does this process do? So basically it has this, you know, here it's called generator function here in this setup. So what does it takes 2 inputs and give us a pair of keys. So what are the 2 inputs here? The first one is called, you know, it's just the function you are trying to prove, right? That's of course right. Everybody, if you are trying to, the prover trying to prove this validity of this evaluation, is at least they both have to agree on what is the function we are trying to prove, right? And also this lambda. I think this one is a little bit tricky. They call it you can think about this a random number for in practice. So it has to add some randomness, you know, because you can think of, you know, if you don't add this, you may not have the 0, 9. You are trying to obfuscate, you know, trying to hide the witness, the W here. So you have to add some kind of like a randomness here. So to give us a pair of keys, yeah, this at the first glance, you may think about, oh, is this like the Bitcoin key pair? One is public, the other is private. It's a little bit different here. So this a pair of keys. First of all, they're made public, so both parties know about this. One is called a approver key. The second is called a verifying key. So both parties, they know both keys, so they have to agree on this pair of keys. Does this make sense? The setup phase?
Yeah, so lambda is only known by the prover.
I think okay.
Where did your robot?
Yeah, that's. Can you say it again? I think there's some background noise or something. I kind of. Brandon, do you want to say it again?
He put it in chat.
Oh,
Sorry. Is the lambda only known by the prover?
I think so. Yes. So here's the thing. So in reality, in practice, usually this is supposed to be carried out by a third party actually. So the third party has to generate this random list, and in the zk space, so they call this toxic waste, because the issue is if somebody gets hold of this lambda later on, they can produce some proof without knowing the secret. So in theory, for zkSNARK to work, some trust third party has to produce this setup phase, and then later on, once they have produced the key of pairs, they have to throw this away. So you probably heard about the zcash. They have this ceremony, and then they are like it's almost like a Satoshi keys, to them. So basically, they go to a debtor, they perform the setup, and then later on, they destroy all the laptops, they burn the hard drives. It's very dramatic. So I think we can later on we can have another episode dedicated to this. Is a very you can think of one disadvantage of using zkSNARK. Basically, you have to have some kind of so-called trusted ceremony. The lambda has to be a secret, and only the guy who produced the setup has to know, and then she must discard it. So think about, this first step has to be carried out by trusted third party, and then the second step is by the prover, and the last step is by the verifier.
So, did you say like that lambda to be discarded, or
it has to be discarded actually in this scheme?
Oh, okay. But how do you? How do you? If you discard it, how do you use that for subsequent, verification yourself? So I think you have to save that, right? Or you have to secure that.
Yeah, basically, the lambda you have to discard it because, So I think let me finish this too, and then we can go back to why this has to be discarded later on. Yes, trust third party. I think okay, we can keep going with this, and then I will talk about ways to get rid of this, or at least alleviate this problem. So let's go to the second step here, and then I think when we finish the second and third step, I think we can come back to the setup and then talk about more about it, and then hopefully it will make more sense. So in the second step, right? So you can think of this is the trust third party produce this, and once you have a key of the pair of keys, then the prover can take three things here. She can take her because she knows the both input X, the public one, and also secret input, the waitlist. And then she also takes, the proving key here. And then he runs through this algorithm. It will just produce one output, which is a proof. Okay, so 3 inputs, 1 output, the proof. Once she has a proof, she can give it to the verifier. And the verifier takes 3 things, right? So be careful here. One is, of course, the verification key, and then the proof, and also because the input, there's a public part called X. Note here, there's a very important thing missing here. If anybody notice here what's missing here? Obviously, anybody compared to prover?
Is it F?
If you compare to the prover, what's missing from the
Private key?
F.
W, right?
Yeah.
You see here? That's a very important part. I think that's the whole point of zero-knowledge proof here.
If I cannot know W, yeah, that's
Yes, because if the verifier knows W, then it's not zero knowledge, right? She pretty much the prover give us the secret input here. So the most amazing part here is without knowing the W, the verifier, if this passes to accept, he can be sure, the prover knows the secret input that make sure this function returns true. So that's the zero knowledge part of it, because this private input only knows by the prover. Okay, so that's I think that's the where the zero knowledge part comes into play, because without knowing this, because if verifier knows it both, right, and he also knows function the F, he can just verify this by running this computation, right? And then there's nothing magic about it. It's almost like if somebody claims, let's say, if you do the square of 9, you get 81, right? And then if you know the function is square, and if you know both inputs, the inputs, there's nothing secret about it. How do you verify this is true? If Alice test Bob says, hey, if you square 9, you get 81. How does Bob verify? Bob just recomputed, right? Then it's not a zero knowledge in the sense, right? And also it's not succinct. Succinct means, also the verifier doesn't have to recompute F, because first of all, the verifier doesn't know the witness here, right? And second of all, even if he knows all the inputs, this scheme makes sure he doesn't have to rerun it, because then you don't need this protocol at all. You can just recompute it. So it's the amazing part is you don't need the W, and the verifier, this complexity is actually exponentially faster than just rerun the computation here. So for example, this is N. If this is, complexity is N, usually this verifier is log of N, or sometimes just constant. I think for zkSNARK, yeah, it doesn't matter how complex this one is, this is going to be constant. So now let's come back to this question of lambda and the setup, because so here's the thing, right? So this algorithm makes sure if this checks out, right, the last step, then the verifier can be sure this returns true. But there's only one exception. What if the prover knows this lambda, and then without knowing that W, and then make sure this producing that true, she can actually, the prover can fake a proof, and then the proof can still pass, but Alice doesn't even know the W, or this function doesn't return true at all. So that's why it's called toxic waste. And this is the one drawback. I think the number one drawback for zkSNARK in practice, actually. So you have to make sure this ceremony has to be kept private, and everybody who compute this, they have to discard this. Okay, and any questions? I think there are probably many questions regarding this setup.
Hey, is my audio better? If not,
yeah, now it's better. Now it's clear.
Okay. Can you reuse the PK and the verifier key? Like, can there be one setup
Good question.
and that just be used?
Okay, the short answer is yes and no. Okay, yes, you can reuse it when the function you are proving is the same. Okay, if you are using the same function, yes, you can reuse it. But if the function changes,
So-
it must change.
So,
Makes sense.
for example, battleship game, you
Uh-huh.
could have one ceremony and just reuse it.
Yes. But then
Okay.
if you use the same scheme to prove, let's say, like a row F, right? Then because the F changes, then you have to redo the thing again.
If what change, how would the
The
function
F,
change?
the F
and-
function changes, right? Because you are proving different functions.
Right, right. But
The-
so
the
battleship,
circuit-
it's
Yeah, battleship is the same, but then it will be different from, let's say, zcash circuit.
okay.
Okay.
Is the function is public, right? That's public information. It can change, but it's public information.
Yeah, it's public. It's almost like yeah, because everything here, this is, yeah, the function, of course, right? It's obvious because, you know, if the verifier is wants to, you know, the prover to show him something is true, right? At least they have to agree on what problem, what statement you are proving, right? Is it like a private key? Is it like a hash pre-image? Yeah, they have to agree on in advance. Yeah, of course. Because
Yeah.
otherwise
So
the verifier doesn't
in
know
order
who is proving.
Yeah.
Then there's no point, right?
so in order for VK to change, you can either change the function or the lambda.
Yes.
Right. So I think from a securing part, like if you constantly change the lambda, and maybe that will secure lambda as well without having to discard it, because the idea behind not discarding is, I think it's going to come in use at a later point, and that's where the cost comes into the picture as well, right? So because if you discard it, you know, I don't know if I'm able to connect, but yeah. So I think for me, like, better solution would be to secure that lambda, because that's going to be useful in the future. But how do you secure the lambda is to create a new one every single time, regardless, even if the function changes or remains the same, you still have secure your I don't know, your information, and still be able to provide the zero knowledge, right? Is that?
Yeah, I think that's one way to kind of improve the security of the whole system, because, you know, if you are reusing this thing, right? So if it's ever being compromised, then people can, you know, use this to fake proofs, right? But if you're changing, I think that's going to be supposed to be to be more secure, right? But then you have a trade-off, right? Because then you are redoing the same thing. You have to, because you change this, you have to redo the thing again, right? And this process. So here's the thing, the rule of thumb is the first step and second step, it may take quite a while. And the last step is very quick, like a millisecond. I think the first and second step, is the bulk of the time when you use the zkSNARK. You pay, I think for normal, I think, yeah, people usually represent this in the circuit, in like almost like a so-called a circuit, like almost like a hardware circuit. You have addition, you have a multiplication. So that's how they represent this F. So when you produce this, the bigger the circuit, the more complex the function, and the more time usually these two takes. And usually for the functions that's been deployed in practice, usually takes tens of seconds. Sometimes it can take minutes. And then when you download the keys, and this key is very short. In zkSNARK, this is almost the theoretical limits, the lower bound. I think it's 288 bytes. So it's less than 300 bytes. So think about, you compress pretty much all the information, doesn't matter how big it is, into almost like 300 bytes. And this, it can be gigabytes. So just give a rough sense. So this process can take tens of seconds. This is tens of milliseconds. And then the size of this thing, this can be gigabytes. This proof and the verification key is all just a few hundred kilobytes, a few hundred bytes, sorry. So it's very succinct. Okay, so I think people asking in the chat. Yeah, agree. I think the trust third party is always not a good idea in the so-called trustless blockchain context. I think that's why, as I mentioned earlier, this is one type of a proof system. There are a lot of newer ones that try to get rid of this. the newer proof system, zero knowledge protocols, that you don't have this. You only have this two steps. You don't have the setup. But then they come with trade-off. You could probably imagine, right? Because you have trust in someone here, third party here. So it's all very fast and very small. But then if you get rid of this, which already people have, then you have a bigger proof, and also it's everything is bigger and more complex. But that's a trade-off you are making, right? So there are ways, there's actually a lot of ways. So the zk, after zkSNARK, there's a lot of, it's almost like a very active research. You have new papers coming out every few months, if not every few weeks. You have new ways, people trying to get rid of this. There are some schemes, but they have some trade-offs. So that's one way. The other way, that people now do it in reality, in practice. They're deploying zkSNARK because they still want the proof and everything to be succinct, small, right? So they still keep this scheme, but what they do is, instead of one party compute this, they do it in a multi-party computation. So basically, think about Lambda. The easiest way to think about is, let's say you have 100 people, right? Everybody produce their own Lambda, and then the final Lambda is going to be the multiplication, the product of all these Lambdas produced individually. So as long as one out of this 100 people throw this Lambda away, then the final number is unknowable, right? So then is safe, supposed to be safe. So two ways, I just give a summarize to alleviate this trust, the trust ceremony. One way is to just use entire new proof system, not different from zkSNARK, and you don't even have this, but you have some trade-off. Other things may become a little bit more expensive. And the second way, I think most people doing today, is multi-party computation. They have multiple people together produce this. So if any one party discuss this, then nobody knows the final Lambda used here. Questions?
Question in the. I'll go in real quick. So in a blockchain scenario, we would publish the proof and the VK, the verifier key.
Mm-hmm. Correct. And the X. These three things will be on chain.
And the X, yes.
Yeah, if you verify it, yes. So yeah, everything here.
And the prover key remains private, or?
Oh, this too can be public. You can be private, it can be public, it doesn't matter. You see here, that's the difference with this key pair different. That's the difference between this key pair and Bitcoin key pair. Bitcoin key pair, the private key must remain private, right? Confidential. But here, both keys can be out in the public.
Okay.
So when you're in the blockchain space, these three things will end up on chain. But this thing, yeah, it's only used by the prover. You can be made up public. It also can be private, but doesn't matter.
So I think about the VK, is that going? I don't think can that be public to every like in the public chain? Like
this one
be public, or or is it only public to your to the peer who you're?
Oh no, it's public. So not only the verifier can see it, everybody can see it and then verify himself. So everybody can see it. It's the same for proving key as well. Everybody can see it. This is public information. It's like the F. Everybody can see it.
So generating the proof, you said it was expensive, right?
Yeah, that's actually the #1 bottleneck.
So, and the problem is that it takes witness data. So you think like you're not going to want to send it to like some cloud. You want to generate client side, right?
Yeah, that's
so is yeah. So how could you, like, if this was to work practically, like there'd have to be some way to send witness data to like a third party that can generate the proof, but without giving it to the third party. Is that possible?
That's a new line of research, I think, which is still very active. Just okay, so let me rephrase, repeat the question, because yeah, very good point. I think now you are like at the cutting edge of the cutting edge. Okay, because I just did the research like a few days ago. So basically, the good question here is because you are trying to, because I just said this process can be computationally intensive, right? And then if you are a client, what if you don't want to, either you cannot produce this proof or it takes a long time, a lot of resource, either in your browser, your desktop, or your mobile phone. What if you don't want to do this, you want to outsource it to a third party? There are some ways. It's almost similar to like, if you heard about the split key, almost like a secret sharing, using the Shamir. Pretty much you just split this thing and then give it to different, outsource, the so-called worker. And then they all produce something, you give it back, you merge, you get the thing. But that's still like a very active research. I think it's not, there's nothing in production yet. This is all theoretical. So basically you can split this thing and send to different workers. They produce different sub-proof, and you give it back, and then you merge the proof. So then, unless all the workers, they collude, they know the secret witness here, and then you can outsource, but you can still make sure this is private.
Would something like homomorphic encryption apply here?
Not really, because homomorphic still it's not. I think there are some special cases you can still carry out the function without the full thing, but still I think this is still not for general problem here. Basically, you can think about this like this key is almost like encode the function. So it's not for certain simple functions you can do like a homomorphic computation just even on the encrypted thing. But in general, this is not a solved problem in crypto. So short answer is no, you cannot use this homomorphic encryption to solve this. Okay, so just now let me repeat. There is some way to, if you have some assumption, basically you send it to, let's say 5 workers. Each one has a slice of W. And if they don't, let's say less than 3 collude, they cannot get this. It's almost like a threshold, not the split key scheme. So you can split, you can treat this as a private key, you can split, and then you have it's almost like a threshold signature. So you can, nobody knows this thing, but the private key itself, but you can still produce like a signature, the proof here. But that's still not realistic today, as far as I know. But so in reality, what does that mean? The implication is this F in practice today, it cannot be too complex. You cannot probably compute, let's say, 1 billion a matrix times another matrix, 1 billion columns, 1 billion rows. You can probably not do this today. If you want to have privacy, does this make sense? So that pretty much give an upper bound on how complex the F can be. If you want to make sure you only can at the client side. But the good news is, I think I'm showing a lot of examples. It's all deployed today, and they all can be run in client side. So this covers a lot of things already you can play with, and the technologies keep improving, right? So the complexity of the function you can prove is just keep increasing almost every day. But of course, as you said, that unfortunately plays an upper bound, like a ceiling on how complex the function you can prove today at the client side without giving out the secret.
Yeah, I remember making a Zcash transaction, like a T-style address, and it takes so long. So it's just, it's like unpractical.
Okay, here's the thing, they upgraded later on. So now I think it's like 3 seconds or something. So at the beginning they call it
I haven't tried.
yeah, it's called sprout. I think now called sapling. That's why I think why I make the comment. The technology is constantly improving. So what, that's slow maybe a few years ago, now maybe it's just 10 times faster. So these things keep improving. So all the algorithm I mentioned here, either software or hardware implementation, it's just keep improving. And also people coming out with new type of zero knowledge that use different algorithms. So it's even faster. So the short answer is, for a lot of things, you can still do it today. You can already do it at the client side. And I'm going to show it later. Sometimes you don't have the private input because you're only trying to use the succinct part. So basically you're proving something without rerunning the thing. For example, roll up, right? You may not always want to hide something. You just want to make it run faster. So in that case, then you can easily outsource, right? Because you don't have private input. That's another big category, I think. Make sense?
So, like when you say the proof generation is that like you said, energy, like costs a lot of energy to generate the proof, a lot of calculations?
Yeah, that's like a correlation, right? So basically, the more computation you produce, the more energy you have to burn, right? So think about this. This is just algorithm, right? I think Manikanran is also asking, these two things: this generator, proof, and generation, and also verification. All these are public. This is like a public algorithm. It's like a ECDSA 6-digit signature. So these are all this algorithm. The function is these are all public, right? This is the algorithm. So this algorithm, the complexity usually is in this sense is, so let's say the F, the complexity is big O N. So this usually is so-called quasi-linear. So it's n log n here. So the bigger, more complex the function is, so this also grows the complexity. So you have to do more CPU instructions to compute this. And then as a side effect, you have produce more energy, but nothing close to like a Bitcoin mining yet. So it just take, let's say 10 seconds, right? Or even 60 seconds on your end device, edge device. So it can potentially produce some energy, but it's not even close to, say, Bitcoin mining. It's different magnitudes, much smaller.
Yeah, because because I was thinking from a perspective of like, because generating the proof is more like a random, event, right? So it happens first, and then you register that into some kind of ledger, and then when the other party verifies it, so that is going to be more energy costly in my opinion than generating the proof itself, because the proof itself is the first event, which is more, like it's a random event, and you can generate anything. The event after that is what should be more like energy hungry, the verification process, don't you think? Or what?
Yeah, from a high level, I think you can think about this way, right? So now, let's say, because if you are the prover, you at least you have to run the function itself, right? You have to execute it, and then you have a little bit of overhead with the n log n, right? Why you have a little bit overhead? Because not only you have to run it, but also you have to generate a proof. So you are doing some additional work. So that's why it's a little bit overhead instead of n. Is n log n. But the verifier, of course, it has to be sublinear, meaning, I can always, rerun the whole thing, but then I don't need this scheme at all, right? If I just talk about how do I scale the verification, because if I have to rerun the thing, I would rather just, I don't need this scheme at all. So it has to be very efficient. So in reality, I think most of the proof system we talk about zero knowledge proof is a log n, or maybe like a polynomial of log n. Does this make sense? So basically the prover has to at least rerun the thing. So it has to be, and then it has to produce, in addition to rerun the thing, it also has to produce the proof. So it's a little bit higher than just rerun the thing. which is why it's, a lot of times n log n. But the verified wants to verify it without rerunning the whole thing and just quickly check it. So usually it's at the level of log n or just polynomial log n. Let's say log n square.
Yeah. Okay.
Okay. And anything else? I think this is a little bit of big slides here. So hardware. Okay. So there should be. Yeah, you can. I think Monica June is asking, you know, is this reversible? No. This is all you can think about. All this non-reversible. Is this a function? It's a one-way deterministic function. So you cannot reverse this thing. No, you cannot remove, because if you know this proof, this is reversible, you can get the W here. No, you cannot. It's a one-way function you can think of. The information is lost. Remember here, right? This can be gigabytes, and this is only 300 kilobytes, right? So even from the information theory side of things, you cannot recover this thing from a small thing, right? Because that's the only thing you can produce. Okay, but good question. Yeah, Maysam, you have can you ask here? Do you want to ask here your question? I'm not quite following you here, the hardware related question. Do you want to ask here? Okay. I mean, I'll ask later. If not, if we can move on. Anything else regarding this slide? Okay, if not, we can keep going. Okay, we talk about the zkSNARK, how it works and what kind of things you can prove, and we talk about a little bit of you know, the different complexity. So let's look at some of the existing use cases. Okay, what have people been doing with this zkSNARK in the crypto space? I think I'm giving out the most famous examples. Okay, just a quick disclaimer. I'm just explaining the tech side of things, so it doesn't mean this is something people should do. Okay, so if you are using Tornado Cash, I'm just talking about the different ideas, right? So for example, the first application of zkSNARK in the blockchain space, I think probably as Brandon just also mentioned, so-called zcash. So zcash, for people who don't know about this, is pretty much just a shielded or anonymous version of Bitcoin. It's also based on UTXO model. So for example, you have Alice. When Alice sends some Bitcoins to Bob, you know, if you look at the Bitcoin blockchain, you can see that, you know, the sender address, the receiver address, and also the Bitcoin amount. Right? So these are all plain text. There's nothing encrypted. It's all plain text. Versus Zcash, if you use a special mode called a shielded address, so you can hide all three things: the sender, the receiver, and also the amount that's being transferred. So when you look at it on the blockchain, it's pretty much like a random byte string. You think about it being encrypted. So the amazing thing about this is, you know, if you hide something without the miners know, how do they know this transfer is legit, right? So for example, how do you know Alice is not creating coins, Zcash coins out of thin air, right? Then you are using the zkSNARK technology. Basically, when the sender is trying to send something, she has to prove, you know, she has a coins, she has a signature, she has enough chain, she has enough balance. Basically, you're proving some function, and this function is pretty much just you're validating the transaction, the validity of the transaction, right? You know, all these things I just talked about. The coins exist, you know, the signature is good and it has not been spent, and you know the inputs is no less than outputs. You know, all kinds of things you can prove. You put it in the function, and the miners, they just verify the proof. Then because you only have the proof. You don't know that all the details. The details are the private information, which is, the W we just talked about, the witness data is kept from public view. But you can still make sure this function is valid. The function here is just transaction validation. Yes, okay. Oh, that's another. I'm not sure about that. Okay, any question here about Zcash? Okay, if not, we can keep going. I think that's another famous example, because now it's been on the news constantly. So a lot of people heard about this recently, so-called tornado cash. So basically it's a smart contracts based mixer running on top of Ethereum. So this is, you can think of it as another layer 1 blockchain, right? So this one, it's just smart contract on top of running on Ethereum. So what does it do? For example, let's say all of us here, about 10 people, right? We each deposit 1 Ether into this smart contract. And then later on, each of us can withdraw 1 Ether from this. But here's the thing, when you withdraw, you can withdraw to any other address. You can generate a new address such that, so if I have 10 people in, 10 people out, each one has 1 Ether. Then you don't know, right? It's kind of you shuffle the source of the Ether is coming from. Then you are obscuring. It's more difficult for people to track. Oh, which of 1 Ether corresponding to, the Ether that's deposited. And also, it also has to make sure, then the smart contract has to make sure, right? First of all, if I don't know who has deposited into this, how do I make sure when somebody is requesting to withdraw, how do I know this one is authorized, right? So it also has to use some hidden information, but also can verify the validity of the transaction here, because you don't want people, you want to do 2 things simultaneously. One, you want to hide some information, keep something private, right? At the same time, you still want to verify, this transaction is legit, right? Because you don't want people, if I have not deposited, I cannot withdraw, right? So for example, if you just deposited once, 1 Ether, I cannot take out 2 Ethers, right? So the zero knowledge is the only way, as far as I know, you can achieve these 2 things simultaneously. So the F function here is also set, it says, okay, this one has deposited money before, and this money has not been withdrawn, and it has a right signature, it has all the right information, right? That's a function is validating and is proving here. If the proof is accepted by the smart contract, the smart contract is pretty much just a verifier, right? So once it checks out, then you can allow the withdrawal transaction, and then you can take your mixed 1 Ether out. But for legal reasons, it's being sanctioned. Any comments and anything here about anonymous transaction, either totally new blockchain or just a smart contract running on existing blockchains? Okay, so far so good. Okay, and that's one type of basically to do anonymous either token or coin transactions, payments. So that's one big use case. The second one is, I think I'm a big fan of this. So I call it incomplete information games. So before zero knowledge proof, right? So if somebody wants to put a game entirely on chain, it's still doable, right? So we produce a few examples. You have tic-tac-toe or your crypto kitties, right? One of the famous example, or tic-tac-toe, or you can play chess, right? Or checkers. For this type of games, the feature is, all the information is public for everybody to see all the time, right? For example, you are playing chess, right? Alice and Bob play chess. Alice can see all the moves of Bob. Bob can see everything that Alice is doing. Right? And the whole board, the state, is also visible to everybody. So that's one type of games people are playing. But there's another big category of games, which is so-called, incomplete information. That means, each player only knows partially about the complete state of the games. For example, all the most popular games of today, right? You think of World of Warcraft, Civilization, or whatnot. What's the latest? I'm not a big gamer, so all kind of, or poker, right? A lot of times you want to play games, you don't want to give out all your information, because then that's not as fun, right? Because think about playing Texas Hold'em or poker, right? If everybody knows everybody else's card, it's not the game just simply cannot be played out, right? Because then you miss all the fun part of things, strategy, game theory, or bluffing, or or your poker face, right? You can miss all the game strategy fun side of things, which makes the game fun at the beginning. So we have, especially for the Bitcoin space, people have been playing with this type of games. So one is so-called a battleship. I think we also produce, interactive tutorial. So that's actually the world's first ever, and even to today is still the only 09 course out there. So if you have not checked it out, definitely check out sql.io. You can go to learn. You find this example. So what is, for people who have not played this game, what is this game? So basically, you have two players, Alice and Bob, and they each have a fleet of ships. Usually it's 5 ships. You have some carrier, you have a cruise ship, you have submarine, whatnot. So you place these ships in a fixed grid board, right? So if 2 phases, once you finish the placement, then you cannot move it. And then each player say, hey, I fire at some coordinate. Let's say I fire at, 3, 2, right? This coordinate. And the other player has to say, hey, is this a hit or not? So if it's hit, they put a pin there. And then the rule is that, whoever guessed and then sunk all the opponent's ship, they won, right? So whoever is, if you guess right, if you're every position of your enemies, of your opponent's fleet, you can sink them all, then you win. Okay. So you can often see from the picture is an incomplete information game, right? Because if you know your opponent's, fleet position, there's no point play this game. There's a whole, is the fun is the guessing and the strategy, right? So if you know the position, you can just fire exactly at the fleet. So then it's generally considered impossible to put this kind of games on blockchain, right? Because on the blockchain, not only is the smart contract code public, right, but all the data, pretty much the game state is also public, right? So that means the position of your enemy's fleet, right? But then there's a dilemma, right? So if you want to play this game on top of, let's say, Bitcoin blockchain, you have a dilemma. One is you want to put the state onto the blockchain, but then your opponent can see it, right? That's not good. But on the other hand, if you don't put the state information there, the miners cannot see it, and they cannot enforce the rules being followed, right? So then zkSNARK is like a magic tool. You can achieve these goals at the same time. You don't put the information on the blockchain. You hide it by just submit a hash of your positions, right? You just produce a hash, you hash it, put on chain. But then you can also, the miners, based in the smart contract, can also make sure, without knowing the private positions, you can also make sure, hey, all the rules are being met. For example, if Alice say, hey, I file at 3 by 3, and then Bob because she's already locked in by the hash, so now he cannot move the fleet, right? So he has to tell, okay, this is a hit or miss. And the good thing about this is, if I'm using zkSNARK, the Bob cannot cheat, right? Because you don't want people to cheat in the game, because if it's a hit, it's a hit. Otherwise, you know, if you don't want to trust Bob to say, hey, it's a miss or not. Right? You want to make sure Bob not only claims a hit or miss, but also produce a proof. And then the game, every time it moves, is a state transition function, right? So every time Alice makes a move, the smart contract has to produce first one the move, and also a proof that getting from Bob, hey, saying this is a hit or miss, and then the smart contract has to verify this. The proof is good, and meaning everybody's following the rules, nobody's cheating. Then you can keep going until, you know, at least one part gets destroyed. Okay, makes sense here? And any questions about the battleship?
Thank you. That was very clear.
Okay, sounds good.
Yeah. Battleship makes sense to me. I have a question about something like poker,
Okay.
where so Battleship, it makes sense that you have like one function and it's simple. But in poker, like I could fold after we see 3 cards, or I could fold after I see 4 cards. Do I need a different function, or is it like one God function that takes care of everything?
You probably need multiple functions, because, for example, you have different phases, right? For example, when you shuffle the card, right?
Right.
To make sure, hey, this is all unique, and there's nothing fishy is going on, and everybody has to make sure that this card has the, let's say, 54 cards uniquely, and then once it's shuffled, you think about this zkSNARK incomplete information game. You are almost simulating the physics, the physical environment, right? So, for example, you are here battleship, you are simulating the, you know, the board, you know, is blocking, you know, your view. So in, let's say, the poker game, let's think about it, right? Walk through this example. First, you have to make sure, you know, the card is shuffled right. That means is you got all the unique cards, each one only appear once, and also you are like putting it on the table face down, right? So you can shuffle, you have to use one function you are proving to make sure it's shuffled is right. And then you probably need some kind of randomness, or you want to make sure if 3 people are doing it, or let's say 2 people are doing it, they both shuffle it independently. So that's one way. And then you simulating, you put the cards on the table face down by hashing, right? You can hash thing. That means now nobody can move the card. And then you're starting drawing card. That's probably another function. Pretty much you're using your cards, let's say 5 cards at hand. You're giving out one, you're taking another one. So you also make sure, let's say this one card you are putting on the table is one of the 5. And then when you get the new one, it is at the top of the deck. Does this make sense? You probably have to, each step, you pretty much you have to use
So
zkSNARK to ensure.
Right, so that'd be like a really advanced. Yeah.
Yes, I think this is
Is there an example?
Yes, I think people even publish papers on this. I think in the show notes, I'm going to put a few examples, and also trying to, people already have some circuit built for this, but it's much more complicated, as you could imagine, than battleship, right? But it's doable. I think it's doable, right? Because as I just said, you just make sure all the cards at hand is all hidden all the time, and then make sure, let's think about it, right? They have some public information, you have private information, right? Public information is, you know, let's say what's already being put on the card, face up the cards. And then the private information is, you know, each player's card at hand, but also what's the remaining deck, right? That face down on the desk. But I think every step you can simulate with zkSNARK.
Is there any usage of zkSNARKs like this in practice, like in like a commercial setting?
Now you are becoming I don't know what happened to the voice. It's just me, or Your voice is
Can you
Darth
hear me?
Vader.
yeah, static. I don't know why, but
Can you hear me, Joey?
yeah, I think it's just Brandon. It's a little bit weird, but everything else, yeah. Oh.
So I
Okay, let me quickly answer Brandon's thing. Yeah, that's an example. I think if you think about commercial advanced application of zero knowledge enabled on the blockchain, the most advanced, as far as I know, is oh, accident. It's just this game called Dark Forest. I think I've been researching this for quite a long time. Non-blockchain. Oh, not really. I think it's zero knowledge has been around for, I think it's since the 70s. So it almost has a renaissance because of the blockchain space, because it's a very good marriage, right? You want to be a smaller proof, but also you want to have a private information on the blockchain. I think outside of blockchain, I think people have been talking about different things, but I've not seen huge adoption. So you can think about zero knowledge is almost the number one application is blockchain today. So outside blockchain, I don't know any real thing at scale in production. No. Okay, Samir, you have something?
yeah. So like for every change of state, will that have to be registered at some some location for that, or like because you mentioned like if even in the battleship game, so when there's two parties, right? So one can keep the secret of their state, but yeah, I mean you can't keep a secret of your state and still be able to verify that later that you haven't changed your state while keeping a secret without registering it to the global like a main ledger or something, right?
Okay, yes. So okay, let me try this. So the game is this. So the ledger, what you mentioned, is just a smart contract, right? When the smart contract first starts, get initialized, gets deployed, everybody, okay, both Alice and Bob, they have to submit the hash of the fleet location for two things, right? One, when you hash it, you can move it, you cannot move it later, right? Let's make sure, because if you can constantly move the ships, you cannot play this game, right? If somebody said, hey, I fire at 4-2, you can always move your ship, then it doesn't work, right? So hash one is to commit to the positions, so you can not move it later. Second, you can then, we're given only the hash, you can always submit your private information, which is your fleet location. And then you can produce a proof, right, later on. So it's two things: commit to the position, but also make sure you can use zero knowledge to prove, okay, this is my position. And if you say hit 4-2, it's a hit or miss. And this is, I'm not cheating. You can produce a proof. And the ledger you just talk about, the state, all this thing is in a Bitcoin smart contract.
Yep. So basically you anchor your position first, and then every change of state that each of those do, you probably send a new hash to the right. Is that what you're saying?
Later on, you don't need a hash. You can just say you can keep a state, right? You can keep a plain text state, right? Say, hey, I got how many hits so far. So for that thing, you don't need a hash. You may use a hash, but you don't have to, because you don't. There's some information you don't have to hide, right? Let's say how many hits you have. Yeah.
Okay, so just first the anchor, and then like any subsequent change of state, you just share the information between the peers itself.
Yeah, you can be public.
Okay.
Okay. Another question? Okay, if not, I just talk about, Brandon just asked about, what's the number one or most popular, most famous application outside blockchain. I don't know, but I do know one that's in the blockchain space, which is everybody's talking about, at least in the zero knowledge space. The name, the game called Dark Forest. So it's based on a sci-fi series, like a trilogy called, Three Body Problem. The second novel is called Dark Forest. So basically, it's a space conquest game. So the setting is, in a universe, you have different players, occupy different planets, and then they can produce, they can do mining, they can send out the ships to explore the universe, and then they want to, attack and conquer other planets, civilizations. The dark forest analogy comes from the idea is, because you are simulating the real physical universe, so you don't want other people to know your planet's position, because then otherwise they can send, they can be a bit more advanced than you, then they can send spaceship to conquer you first, right? So you don't want to give out your location. So the energy is, you have a, think about you are you are in one tribe in the ancient, I don't know, 3,000 years ago. You are in let's say Amazon. You don't know where other tribes are. You don't want to give out your location, because then other tribes may come here and take all the positions, kill you, right? So you are almost in like a dark forest. You don't want to give out your information, but also you want to explore the forest, right? So, but you don't want to make sound, because you don't want your other tribes, you don't know whether they're friendly or they're not, right? So same here. The one key property is you want to, you want to claim you own this planet, but you don't want to let everybody know you have this planet. So it's almost like a exploratory game. So unless you go to some coordinate or some, again, it's like, think about this universe as a grid, right? Unless you explore some grid, you don't know whether there's a planet there or what properties this has. So here you have a dilemma again, right? Similar to Battleship. So you want to commit, you want to claim ownership of some planet, but you don't want to give out exact location for the planet. So think about that, all this planet, the whole board is in a smart contract, right? Because if you put in location there, then everybody can look at the smart contract and then know where you are, right? So on the one hand, you don't want to give out your location information. There's just one type of information you want to hide. And the second is you want to still make sure, okay, you're not cheating in the game. For example, let's say, you claim you have this coordinate, this planet, but this planet is already taken by another guy. You cannot have two people have the same position, right? Because then you like the game is just the state is invalid, right? So you want to make sure you hide the information, but at the same time you want to make sure everybody is following the rule of the game. For example, you can say, hey, I claim a new planet, but the known universe is only 100 by 100, right? You cannot claim, hey, if you submit a hash, you cannot. You also have to produce it. Even produces hash, this hash is not a random string, right? Because what if I just say, hey, I have a planet as, outside of the known universe, then it's not good, right, for the game. Or you are saying, hey, I'm sending spaceship from A to B, but then you may have a constraint, say, hey, you cannot move ships faster than the speed of light, right? So you can enforce all kinds of, game rules without giving out your exact game state, individual game state. So this is very popular on Ethereum. So it's so popular such that once they launch it, and then a lot of people play, and then again, it's like the pattern we have seen in other blockchains. Then whole Ethereum gets stuck, and the fees went through the roof, and nobody can play anymore. So they have to move it to some side chain, and then later on now XDAI side chain. Then later on have to move to some like not that decentralized, not that secure Genosis. I think that's the latest I've known. So it'll be great if somebody, this is the perfect use case for Bitcoin, because we can do zkSNARKs. You pretty much just swap out the underlying blockchain part, and this is open source, by the way. So you can fork it and then just swap the blockchain part, and then everything will just work flawlessly. I think at the peak they have 1,000 players, and then they pretty much get the whole blockchain, Ethereum blockchain to a halt. So we can support much more than that even today. So if anybody who's watching this, you want to do some side project, this is a very good start. Any questions about this? Dark Forest, but they have a lot of I like them because they're exploring a lot of the frontiers of zero knowledge. I'm going to send some links to them. They're pushing the boundaries. They're doing all kinds of, like, let's say, procedure generation. They're doing recursive SNARKs in the circuits themselves. They're holding conferences and study groups. I think this study group is partially inspired by them. So credit to them. But the everything is good, but except the chain they're using is not scalable. So that makes it, you can not play it like smoothly. For example, they don't have zero instant transfer information, right? So you have to make sure every move you have, it has to be mined. So that's, at least you have to wait for like 15 seconds or 30 seconds, which is not great, game experience, right? If you play any kind of real-time games. Any comments? I think this is the last example I want to introduce. Anything? Nothing? You all heard about this game? Okay, if not, I think it's time to wrap this up. Already like went a little bit of overtime, so 90 minutes and counting. So any final thoughts, closing remarks? Anybody?
I thought this was a great session. And if I would like to do this stuff more often. If we are going to do that, if we could just get a longer heads up, that'd be awesome.
Oh yeah, great.
To plan.
Yes, I think I'm planning to do this every Friday at the same time. So if unless anybody has other constraints, time zone, whatever, I think I'm going to stick every Friday at this time. We can keep it doing as long as people are interested. So there's no cap. Okay. Any other comments? Okay, if not, we can call it a day today, and I'm going to upload this to YouTube and send them a lot of show notes so people can check out. So for people watching later, we just released a repo called Awesome Zero Knowledge. I think I'm going to put the link in the show notes. So it's just all the background materials if you want to know more, and we'll keep updating it. I think we'll even put the study group, the YouTube link over there, so people can always come up. And the ideal scenario will be we'll just keep exploring this, and then people get more ideas, what kind of things people have built on other blockchains, and either we can port them, or the even better ideas will be, people coming up with some new ideas using this zero knowledge, and they build completely new type of applications on Bitcoin. So until then, see you next time. I hope more people can join us. Okay, great. Thanks, guys. Enjoy the rest of the day. Okay, I pause here. See you next time. Okay, Brad, Dave. Okay, Zach.
Thanks. Bye.
Hi, Taylor.
Thank you. Bye, guys.
Okay, bye-bye. See you next time.
Bye-bye.
Bye-bye.